something that a colleague and I, Carlos Nevis, it says RSGB there. He now works for Ofcom as a regional engineer. So he's gone from being poacher to gamekeeper. He's a very good friend still. This was presented at the AMSAT UK stroke RSGB convention a couple of years ago. We normally do this. We used to do this as a sort of warm-up presentation. So I thought I'd give it to you as well. It's well worth. There's some interesting slides in it. So we're going to cover a little bit of what OSCAR is, some of the history of amateur satellites, a bit of theory, satellite operation, satellite modes, the ground station equipment. What's up? This slide set is quite old, so I'll skip over that bit and move on to another one. But I'll go through the highlights of these slides. Okay. First satellite was Oscar 1, just after, well, not long after Sputnik went up. And it's a very strange shape. Imagine an annular ring around the top of a rocket. In the early days, they had to do mass balances and they put lumps of concrete on the top. Some of our AMSAT colleagues in the States said, well, instead of a lump of concrete, can we put a CubeSat on, or so, put a satellite on that will actually take up one of those spaces on the ring? So they came up with OSCAR, Orbital Satellite Carrying Amateur Radio. It had a set of batteries, and it was just a beep sat, and just had a very, very simple beacon. As I said, it sent did it, which is HI in Morse, high. It made 312 orbits, and a lot of the beacons, even on satellites now, the simplest thing that they do to say I'm here, the hello world signal, is did it, including AO40, which is one of our largest satellites. As I said, Sputnik 1 was just a beep sat, and we followed that. But 1957 to 1962, 5 years, and amateurs were putting things in space. How we design a satellite. A receiver, a transmitter, I say an IF matrix. So basically, you can have multiple receivers and multiple transmitters. We have an IHU. The thing about the IHU is it doesn't have to be complicated. It doesn't need to be a high-performance processor. It doesn't need to be something that's small-featured and running at a gigahertz. Something that runs at 40 megahertz has a small number of operations it can perform. The biggest problem with IHUs and any hardware that's going into space is our cosmic rays. Cosmic rays can cause bit upsets within the memory, within the IHU. So the larger the features are within the device, the less likelihood you're going to get a cosmic ray event. You could get a single event upset, but most of these devices now have cyclic redundancy checks. So we can actually keep an eye on the device. If we detect a CRC failure, we can do a reset. And it's as simple as that. FunCube, we've had in 10 years, I think it's 6 single event upsets, and she's come back every time. Maybe once you've had to give her a kick, but she's been extremely reliable. Around the system, there's a power bus, an attitude torque, maybe, solar panels, of course, and batteries. Depending on the size of the satellite, 1U, which we have for FunCube, we've got very little power on board. The transmit is only about 400 milliwatts for the transponder, or full power telemetry. As you go up in size, the more things you can do. You can add things like attitude torquers to actually stabilize the satellite. This is a very basic version of it. As you can imagine, they're much more complex than this sort of small image. We have two types of transponder on board in terms of communications. A single channel FM repeater, basically it's a bent pipe. In other words, whatever you send up to it, you receive. So there'll be an uplink on VHF and a downlink on UHF. There may be what's called a CTCSS tone. So maybe to activate the satellite, you've got to send a subcarrier underneath the spoken voice to keep it alive. The other types are linear transponders for things like single sideband and data with an uplink and a downlink and a mixer in between. So again, up on VHF, down on UHF. I think the next slide goes a little bit more into it. I'll check in a second. But basically, we have two types. These days, we can do more digital modes. The problem with digital modes is that they're very narrowband, and we end up with the Doppler shift. The operators for FM repeaters are fairly lucky in terms of what the Doppler shift is no more than about 15 kilohertz, but you can do that by just changing memories on a handheld. For the linear transponders, you've got to have computer control. You've got to be within a few hundred hertz. Otherwise, you drift apart. You drift on the uplink or you drift on the downlink. So we have something called the one true rule, which basically you track absolutely everything. I'll go through some of the terms that we get involved with. The orbit, again, it's a path around the Earth. Doppler shift. It's in terms of what terrestrial thing. It's the ambulance whistle as it's coming towards you, and as it's going away. The same thing happens at RF frequencies. We have low Earth orbit satellites, high Earth orbit, and geostationary, geosynchronous. There is a slight difference in the two terms. I've talked about uplink, where we talk to transmit the satellite, the downlink, where we receive. The footprint, I'll talk about. I'll give you a more graphical representation in a couple of slides. Apogee is highest altitude, perigee is lowest altitude, and the inclination, in other words, the angle at which it goes around the Earth. We normally talk about something like a polar orbiter. So the inclination is at 90 degrees. Equator is 0. We are at about 52 degrees, so we see an awful lot. We get the benefit of seeing an awful lot of satellites. The threats to satellites, the biggest problem are the Van Allen belts. There are two belts. The LEO satellites live within the belts, so we don't have a problem. For high Earth orbiters, you end up at least 4 or 5 times a day going through these belts. And I talked about cosmic ray problems and radiation. You end up with dosage. The substrate of the silicon or whatever the dye is will actually get loaded with radiation, and as over time the performance of your integrated circuit will degrade because they've been irradiated. Talk a little bit about the sort of orbits we use. This is AO 40, the largest loop there you can see. AO 40 was quite a significant satellite. We lost it about 15 years ago because of a faulty battery, unfortunately. We're out beyond the Clark belt, the geostationary belt. The predominant number of our satellites are in LEO, in low Earth orbit, but as you can see, there's a difference in terms of timing. FunCube-1 is about 95 minutes for its orbit. We see it about 12 times a day, but as the Earth rotates, it's low on the horizon, it comes up overhead and disappears again as we see it. That was the benefit of AO40. It was in the sky nearly all the time, but it was about 60,000 kilometers away, as the geostationary belt's about 32,000 kilometers. Bit of a challenge to get to it. It's even with amateur equipment, we managed quite well. I talked about inclination, anywhere between 0 and 90 degrees. We talk about the footprint, which I'll go into a second. The thing we have to consider with our satellites is because they're so small, that we need a lot of sunlight. So they're launched into what's called a sun-synchronous orbit. In other words, the orbit is inclined such that it faces the sun with the Earth rotating underneath it. Hence, as the Earth rotates and as the satellite's going round, we see about 12 passes a day. We'll see 95 minutes between passes, but then there'll be a gap of something like 9 hours before we start seeing those passes again for the 95 minutes. That's the sort of inclination we might get. That looks like it's fairly low. It's just about going over the pole there. The large circle you can see is what I've called a footprint. It's what the satellite can see at any point in time. So that's somewhere probably over Hawaii, I think. So somebody in Hawaii can talk to the west coast of the US with that satellite in its current position. Some of our satellites, we can actually work transatlantic. So I work from home into New York on a MEO satellite, not LEO. It's actually quite a bit. It's a little bit higher, and that's a satellite called RS-44. And as I mentioned before, we have various types of satellite. RS-44 is a linear transponder, so I have to have computer control for the uplink and downlink to compensate for the Doppler, and I've also got to have antenna control for the pointing of the antennas. This is a orbit called Molniya, which is a Russian derived orbit. I mentioned a satellite in my earlier presentation called Integral, and Integral is in a Molniya orbit. So it's actually doing a lot of work with the Earth's magnetic field. So it's actually not in a fixed orbit like that. It's that the orbital ellipse is actually rotating as the Earth is rotating at the same time. So the orbital elements for that are quite challenging, and the tracking of it, if you actually look at it on a 2D representation, is weird. But unfortunately, I couldn't find a presentation of it, but I'll try and dig one out. This is what AO40 can see, and any similar satellite, it can see a half hemisphere of the Earth, whereas a conventional polar orbiter can only see a small footprint. That's most of the United States. That's very similar to what RS-44 can do. So if the Earth moved to its left, we get right across the Atlantic. People say when we're doing a demo, any chance you can do a demo at a particular time? No, I can't move the Earth. We've got to wait until the satellite comes over. I'll tell you more about those problems in a little while. I mentioned AO40. She's an absolutely wonderful satellite when she was working. The gentleman on the right-hand side there is my colleague, Peter Gulzar, who's the president of AMSAT in Germany. You can see how tall he is. And if we turn the satellite on its side, it's bigger than Peter is. All the antennas on the top of there, I talked about a transmit and receive matrix. I think there were a mixture of something like 24 possible combinations of uplink and downlink. AO40 had a small problem. You can see on the top of the satellite there is a thrust bell. In other words, most of the content of the satellite was fuel cells, hydrazine fuel cells. So that caused even more sort of challenging problems for fueling. On the other side, there's another thrust bell. The idea being that when it was at perigee, after the satellite is stabilized, they could fire one of the rocket motors at perigee to push it out to its highly elliptical orbit. The idea being that so they get thrust at perigee, and once they got to apogee, they'd fire the other one to slow it down to get to its particular position. Unfortunately, somebody forgot to look at the remove before flight label. That's the story. That's how the story goes. On the apogee rocket. So instead of firing, it actually blew the side of the satellite out, which was quite spectacular, I imagine. But despite that, she continued to work for 2 years. We lost a lot of the transmit matrix, and I'm sure we lost a couple of solar panels as well. But a lot of redundancy. She was an amazing satellite. Thank you, Peter, for your design. I talked about Leo. This is AMSAT Echo, not quite a multiple of a 1U CubeSat. This was done in conjunction with a commercial organization who wanted to test some of their hardware, particularly solar panels. This was done with AMSAT North America in conjunction with them. And it worked extremely well. I think it had a lifetime of something like 8 years. Oops, excuse me. It had a lifetime of 8 years, and we could do transatlantic FM contacts through it reasonably well, providing you were sort of on the west coast of the UK, on the east coast of the US. We could actually get through it. I've talked about CubeSats. This is Delphi N. We also have Delphi C3. Which was done by the University of Delft in the Netherlands. You can see it's a little bit longer than FunCube-1. That's 3U. A unit is 10 by 10 by 10. This will be 300 by 10 by 10. And because it's actually, I think because of the image, the solar panels will tuck into the side of the satellite just before launch. I showed you earlier that they're launched out of a pod. That will have fitted in the pod with the solar panels collapsed down the side. There have been historically student satellites. This is PCSat-1, done by the US Navy Academy in the US. Every year, for quite a few years, they had an academic program where they brought their lieutenants through the system, through the educational system, and part of their project, their engineering project, was to design a satellite every year. That most of them never got launched, but it was part of the exercise of doing the mechanical engineering, the software engineering, the RF engineering. So when they went out into the forces, they had a good idea of what the processes were for actually doing something practical. It mentions there the APRS protocol, the automatic packet receiving system. I probably got that wrong. APRS is a standard protocol that a lot of satellites use for transmitting telemetry. It's also used in terrestrial operations for tracking. It's still in use today. Note what the antennas are. If you look closely at the screen, you can see there are numbers on them because they're tape rolls. And I'm sure that you've all played with bending a tape measure back against itself, and it's springing it back. If you've got a tape measure and you've got the numbers on it, you can actually measure exactly what a quarter wave is. And these are tucked up in the around the satellite for launch. Even CubeSats use them these days because they're so reliable. I talked about operation of satellite. We have a variety of frequencies that we can use: VHF, UHF, L-band, and S-band. S-band is becoming more of a challenge now because that's what 2.4 gigahertz Wi-Fi is on. So there's a lot, and we also have a problem. L-band now is because that's what the Galileo constellation is using for GPS. So we're limited now to VHF and UHF, and we're doing a lot of X-band now at 3 centimeters at 10 gigahertz, which is an interesting frequency to use. An awful lot of Doppler at that frequency. I'll talk a little bit about ground station equipment. Handheld antennas. This is Delphi C3, which I've talked about Delphi Next in a previous presentation. Good for portable operations and summits on the air, etc. The guys here, this was at an AMSAT event about 15 years ago, and this was literally the first time they'd heard the satellite go over. It had been commanded on in the Netherlands, and these are some of the engineers that were actually on site at one of our AMSAT events, listening to their first telemetry coming down. We had a few beers after that. Your antennas don't have to be too complicated. This is one of my friend Heather's piece of wood and bits of doweling, and I think they're probably bits of coat hanger as well. Your antennas don't have to be all that complicated. And then you become very silly. This is my friend Howard, G6LVB, in the early days of AR40. So he's got a 77's antenna sticking out front and a 10 gigahertz antenna behind it. And yes, that is an umbrella. He'd actually taken the umbrella cloth off and put some copper mesh onto the antenna, and it worked extremely well. Keep it simple, stupid. I'm not saying Howard is definitely not stupid, but it worked extremely well. Simple things work. Again, this is Howard's setup at home, and very similar to mine as well. So what you can see there on the left-hand side are a pair of WeMo antennas in a cross configuration. And there are 2 coaxes coming off the back of each. Depending how you phase them between them, you can get left hand, right hand, vertical and horizontal polarization just from that one antenna. On the right hand side is the variant of his umbrella. I think it's actually a commercial mesh disc with running a patch feed on 10 gigahertz. And a lump of bags of rice on the back to counterbalance the parabolic dish. The rotator underneath is what we got is the G5500, which is the ubiquitous amateur radio rotator that gets used by an awful lot of people. Very, very good. I think I have to say I've had 3. Because in continuous use, like mine are, the bearings wear out, or feedback potentiometers wear out, and you end up with either the azimuth failing or the elevation rotator failing. So I've always got spares. We've got one at Goonhilly now, and I'll talk about that in a second. We went a little bit bigger with this one. Same principle. It's a pair of UHF antennas, a pair of VHF antennas, and a much larger rotator. This one I think is STEC in the Netherlands, which is the headquarters of East Education, amongst other things, at Noordwijk. This is on the roof of one of their buildings. So it's got a pair of M2 antenna, M2 rotator. It was part of the GENSO network. Well, GENSO is a global educational network for satellite operations. The idea being that universities and academic institutions could contribute antennas to the system, because you only, as I said before, you only ever see your satellite 12 times a day, sometimes good passes, sometimes marginal. And if your antenna is not doing nothing, is doing nothing, you might as well assign it to somebody else's work. Hence the network. That spun off into a lot of other ideas, and it's now called ground station as a service, or ground segment as a service, and there are commercial organizations doing that now. I'll talk about pieces of equipment. This is the THD-7E, which is probably about 15 years old now, as a handheld, dual band, VHF and UHF. With a handheld antenna, you can work most of the FM satellites. As I said, this set of slides is quite old now. One of the earliest radios was an FT847, dual band, and full duplex. In other words, you can retransmit and receive at the same time. No longer in production, unfortunately, but it was an extremely good radio. TS2000 is what we use for the ARIS contacts when we talk to the International Space Station for schools contacts. We have two of those, a primary and a secondary. When it was designed, it also had a birdie. It had a spurious emission on the SO50 downlink, and despite the best efforts of Kenwood, they never got rid of it. So we actually lost one satellite. Well, we lost the use of one satellite, but it's an extremely good, extremely robust radio. These days, you have the likes of the IC9700, fully computer controlled, a software-defined radio inside. That's what we use at Goonhilly for our station. I'll tell you more about that in a little while. The sort of intermediate one that moved on from the TS2000 was the IC9100, almost built specifically for satellite operations. I've got two of those. All ones were deaf. The joke is that they sold them with the RF gain turned down so that ICOM could then sell you your preamp up the mast. That's how the story goes. Mine wasn't deaf, but I still had a preamp as well. This is the ideal ground station for LEO, computer controlled with a 5500 rotator. And these antennas on the right hand side, I think it's 22 element on the VHF. And probably the same on UHF, but it's you can't really tell from that photograph. The problem with these rotators is you've got to balance them correctly. The one on the left-hand side is actually providing all the balance front and back, so you're not torquing it too much as it goes horizontal.